Hello again, 8th grade physics. We are now going to talk about Ohm's law in parallel circuits compared to series circuits. It's a little more complex with the parallel circuits, so let's get started. First thing, when we talk about parallel circuits, we're really referring to a circuit in which current can flow through more than one path. So for example, in this diagram below, we have a path that current can take across this first light bulb, out the positive terminal into the negative. For the second light bulb, the current can go out the positive terminal through the second light bulb and then back into the negative. And lastly, it can go across the third light bulb out the positive into the negative. So there are multiple paths for the current to take in this circuit, making this a parallel circuit. So with parallel circuits, we really are talking about any circuit where current can take multiple loops, and this is going to differ from a series circuit, starting with the voltage. So the voltage in a series circuit, if you remember, is added linearly. The voltage in a parallel circuit is actually the same for all the parts, which is kind of the inverse of the series, because in a series the current is the same, but now in a parallel circuit we are going to refer to the voltage being the same. Why is that the case? Well, the amount of voltage is determined by the battery, which is a difference of potential between the positive and negative terminal of the battery. So if you go out the positive terminal and then back into the negative terminal, that will equal your total voltage. But it is independent of what path you take. You will have the same change in voltage no matter what path you take, which is why the voltage will be the same for every part. So we can represent the total voltage in the circuit being equal to the voltage across the first resistor, second resistor, third resistor, so on and so forth. Now, when we talk about current in a parallel circuit, current will actually add linearly. So voltage and current are essentially flip-flopped in terms of how you analyze them for series and parallel circuits. So because you add the current linearly, you can say that the total current will equal the sum of the current across each resistor. Now, the total current can still be calculated using the total voltage over the total resistance. And again, the total voltage is determined by the battery or the power supply. To calculate the total resistance in a parallel circuit, we actually see something a little bit different. The total resistance adds inversely. So what it means to add inversely is as the amount of resistors go up, so as I add more of these resistors, the total resistance will actually decrease. So how we represent that mathematically is the inverse addition of the resistances summing to the inverse of the total resistance. Now this looks quite complicated, I recognize that. So let's rewrite this in a way that's a little bit more simple for us to use and analyze. So the total resistance, you can actually add 1 over R1 plus 1 over R2 plus 1 over R3 plus however many other resistors you have in your circuit. And once you have that value, so you'll add really all of these fractions, and once you have that, you'll just take the inverse of that, which is the same as saying 1 divided by whatever that value was inside the parentheses. So we'll get some practice with that as well. Now, to kind of bring home the fact that the voltage is the same for all parts of a parallel circuit, I want to make a couple analogies. So when we talk about voltage, we're talking about really the potential energy that the circuit contains. And a good way to make that comparison is by comparing a circuit to a gravitational field. So let's say we have mass 1, mass 2, and mass 3. These are all raised to the same height, okay? So the amount of gravitational energy is mgh, right? Where m and g, if they all have the same mass, we'll give them whatever that value is, and the height will determine how much gravitational energy is. If these guys are all at the same height, they'll have the same amount of potential energy. Object 1 might fall in taking that path, Object 2 might fall taking this path, Object 3 might take a spiral path. Although all three of these paths are different, they all start and end in the same place. Same kind of concept with the battery. The charge starts at the positive terminal, and it could take any one of these three paths, but it will always end at that negative terminal. So because the energy is the same for whatever path you take, since they start and stop at the same points, you can say that the voltage will be the same for all of the parts of the circuit. Another way you can think about this is by comparing it to the water pressure shown in the dam above, where the pressure is the same no matter what outlet you choose. So whether you're taking this first one or one down here or somewhere in the middle. Because the path does not affect how much potential energy there is in the circuit, the voltage will be the same across all of these parts, just like the water pressure is for all those different spouts. So, to summarize, let's really just talk about the properties of parallel circuits. We have a parallel circuit when you have current that can move in more than one element or more than one loop. The more light bulbs you have, the brightness actually stays the same because the resistance decreases. So that's the key difference between parallel and series circuit with resistance. In parallel circuits also, the voltage is the same in all the light bulbs, but the current is different. So why is this difference significant? Well, that's because this allows you to power multiple lights without using a ton of power. So you could have a switch that turns this one off, but not that. So most buildings are actually wired in a way that allows you to create circuits that are in parallel. So far more useful to have parallel, a little bit more complex than with the analysis. So let's talk about how to analyze a circuit that is in parallel. First thing we want to identify is that the voltage is the same for all the components. So right away, if I know the voltage, which I'm given here, I can note that the voltage across each resistor will be equal to 60 volts. Boom. So I right away can fill in 60 for all of these different voltages. Good. Now, because the voltage is the same across each resistor, we can now work on determining the total current. Oops. Actually, let's start by looking at the equivalent resistance. So the equivalent resistance, or the total resistance, will be added inversely. So let's look at what that looks like actually, okay? What we're going to do is we're going to take the total resistance and we're going to add all of the inverses of each resistor. So 1 over 17 ohms plus 1 over 12 ohms plus 1 over 11 ohms. Close that parentheses. And let's actually just find out what that value is. So I'm going to hit clear, and it's going to be important that you type this into your calculator accounting for the order of operations. I'm going to start with my parentheses. I'm going to have 1 divided by 17, that's representing the fraction, plus 1 over 12, plus 1 over 11. Oops, not percentage. 1 over 11. And then I'm just going to close that parentheses, and I get approximately 0.233. Now what I want to do is actually take the inverse of that, which means I want to take that value and divide it into 1. So I can do 1 divided by 0.233. That's just an approximation. So my total resistance is approximately 4.29 ohms. There. Now that I have my total resistance, I can actually calculate the total resistance. The total current. And the current will be the sum of all of the individual components added together. And for each individual component, we can just divide the voltage across that component by the resistance at that component. And it should also be able to be calculated using the Ohm's law relationship between the total voltage and the total resistance. So we know the total voltage. We now just calculated the total resistance. So we've got 60 volts over 4.29 ohms. And we can actually use our calculator to determine that one more time. 60 divided by 4.29, and that gives us approximately, let's just round that to 14 amps for the current. 14 amps. So all these three should add up to 14. Now, in order to calculate all of these, we're actually going to need to utilize the relationship outlined here, the voltage divided by the resistance at each. So the voltage for all of these is going to be 60. The resistance is just going to be the resistance at this particular point in the circuit. So for point 1, we're going to take 60 and divide that by the resistance of 17. So that's going to be approximately 3.53 amps. For the second resistor, we're going to take 60 and divide it by 12, which gives us 5 amps. And then the last one, we're going to take 60 divided by 11, which gives us approximately 5.45 amps. Let's make that 5 a little more clear. So now, again, we can fill in the total or equivalent resistance here as 4.29. If we add all three of these values, let's see what we get. 3.53 plus 5 plus 5.45. That should, in theory, equal the total current that we calculated earlier of 14, and we get approximately 13.98. So that, because these are rounded a little bit, is close enough for me. So now we have found a way to calculate the current, voltage, and resistance at every part of a parallel circuit and a series circuit. So you will need to know how to do these for your unit test and your final exam. You'll get some practice on this on worksheet 3, the back side of it, which is what you should do after watching the videos. So make sure you watch first Ohm's Law video from last week, then Ohm's Law in series, and now this video, Ohm's Law in parallel, and you should have everything you need to know for the worksheet 3 back page, along with studying for your test. Good luck. Please ask me if you have any questions or visit office hours, and let's finish strong.